Okay, today we're going to talk about formal charges and resonance structures. So first with formal charges, it's the charge on an atom assuming that all atoms equally share electrons in bonds. This is going to be important to know whether a Lewis dot structure is stable or not. There's a little note here. Just make sure you realize that formal charges are different than oxidation numbers. Oxidation numbers are determined by assuming that the most electronegative atom gets all of the electrons in the bonds. So we're going to do that they're equally sharing their electrons. So it's kind of done for different reasons. The formal charge we're going to be able to figure out by just taking our valence electrons for that atom minus the number of assigned electrons to that atom. To figure out the assigned electrons, all you do is any lone pairs always are assigned to the atom that they are on, and the electrons in bonds are split in half because we want to make all the electrons equally shared in the bonds. So half of the electrons go to each of the atom around that bond. So I think if we just look at an example, I think you'll be able to figure out how to put in formal charges pretty easily. So let's do this example with CO2. So CO2, it tells you there are two possible legitimate Lewis dot structures for CO2. So we're going to draw those two Lewis dot structures. So you've probably drawn CO2 before. If you draw the Lewis dot, you should get a Lewis dot that looks like that. And then that's the one with two double bonds. There is another structure where you put a single bond to one of the oxygens and then a triple bond to the other oxygen. That also is a legitimate Lewis dot structure. Both of them have octets around every atom. You have the right number of total valence electrons in there, and so they are legitimate. But one is more stable than the other. So we're going to figure that out by putting in our formal charges. So to put in formal charges here, we're going to look around each atom. So this oxygen atom, it has a total of 6 valence electrons. And now we want to figure out how many assigned electrons it has. We're going to count all the electrons in the lone pairs. So that's 4. And then we're going to take half of the electrons from the bond. So we're going to only take 2 more. So 2, 4, 6 electrons are assigned to the oxygen here. So minus 6 assigned electrons. And so that gives you a total charge of 0. So that oxygen has a 0 formal charge. This carbon has 4 valence electrons, and it's assigned 1, 2, 3, 4. So we're cutting those in half, those bonds, and so the carbon is assigned 4 electrons are assigned to it, so it obviously also has a 0 formal charge. This oxygen is assigned 1, 2, 3, 4, and then 5, 6. So it has 6 valence electrons, and it's assigned 6 electrons, and so its net formal charge is also 0. So this is a very stable structure because its formal charge is 0. So when you get close to 0, the closest you can get to 0, the more stable the structure. So that's why this is the structure of CO2. If we look at this structure, it's not going to come out to 0 for all of our atoms. So let's see if we can get our formal charges. This oxygen here is assigned, it has 6 valence electrons. And how many is it assigned? 1, 2, 3, 4, 5, 6, and then one of them from the bond. So it's assigned 7 electrons is assigned to it. So we subtract those 7 and you get a -1 charge. So we're going to write a minus up here on that oxygen to show that you have a -1 formal charge. It should make sense. This oxygen is assigned 1 more electron than its normal valence electrons. It has 7 electrons assigned to it instead of 6, and so it's got 1 more electron, and so that gives it a -1 charge. That's another way of thinking about formal charge. This carbon here, 4 valence electrons, and it's assigned 1, 2, 3, 4, right? Because we're cutting those bonds in half. And so it's assigned 4, 4 electrons that's assigned, subtract, it does have a 0 formal charge there. Okay? This oxygen has 6 valence electrons normally. It's assigned 1, 2, 3, 4, 5. So 5 electrons it's assigned. And so subtract, and so it's +1. So we're going to write a plus on that oxygen there. So overall, it comes out to be a neutral charge overall, which CO2 is, of course, neutral, but it has a -1 on this oxygen and a +1 on that oxygen. Again, this has a +1 because it's assigned only 5, but it normally has 6 valence electrons. So it has 1 fewer electron than normal, and so it has a +1 charge. So you can see this is a lot less stable because the formal charges are not as close to 0. So this is our stable. This one is most stable. Well, let's say more stable. And it turns out in this case, when you have no formal charges, that just makes it so much more stable. So really, CO2 really looks like this structure, and it really doesn't look like this at all. Okay? So formal charges can help us see whether a Lewis dot structure really is very stable or not. Okay? We're going to be using formal structures again, formal charges, I'm sorry, when we do resonance structures. So now let's look at resonance structures. So sometimes there are multiple legitimate Lewis dot structures with reasonable formal charges. In these cases, the actual structure of the molecule is a blend of all these possible resonance structures. So sometimes, kind of like this situation, you have 2 structures that are possible. In this case, this one has so much better formal charges. It exists as CO2 with the 2 double bonds, and it doesn't exist as this one here. But sometimes the formal charges are very similar, and so the molecule can exist, is represented by these multiple resonance structures. So anyway, let's see if we can draw the resonance structures of O3. So O3, if you do a Lewis dot of O3, you can get a structure that looks like this. Everything has an octet, and we have our total 18 electrons, which is what we need. Now, of course, we can draw this another structure. Instead of having the double bond with this oxygen, we could put the double bond on the other side with that oxygen. So let's draw that. And some people say, wait, that's the same structure. It's really not, because in O3 there are 3 oxygens. So which oxygens get the double bond? Which oxygen does not? If we label this like oxygen A, oxygen B, and oxygen C, is there a double bond between A and B? Or is there a double bond between B and C, right? So what actually exists is, it turns out that it's actually a blend of both of those structures. So what we do is we put this double-headed arrow in between those structures, and you put brackets around those structures, and we say that these are the 2 resonance structures of O3. There are 2 structures. In this case, they're equally favored. We're going to put in some formal charges to prove that. And so the real structure is really just a blend of the 2. And it's not like the structures are going back and forth, back and forth, back and forth. That's not the case. It's just mathematically, they are really just mixed together. So what we can do is we can imagine them mixed together, and we're going to get a hybrid structure is going to represent real molecule. Okay? Now, the hybrid, in this case, these are going to be equally favored. Now let's prove that they're equally favored. If we put in some charges, formal charges here, this oxygen has 1, 2, 3, 4, 5, 6 electrons assigned to it, and it normally has 6 valence electrons, right? So that's a 0 formal charge. This oxygen has 1, 2, 3, 4, 5 assigned to it, normally 6, so it has 1 fewer, so that's a positive charge that's assigned to it. This oxygen has 2, 4, 6, 7 assigned to it, that's 1 more than normal, so that's our minus formal charge there. So same idea happens over here. This one with the single bond turns out to be negative. This one in the center here is positive, and then this one has a 0 charge on that oxygen. So you can see you have a +1 and a -1 in both of these structures, but they're equally favored, right? Because they have the same formal charges. And so in this case, we're going to equally blend these two resonance structures. And so what happens is you end up getting a structure, and you can try to draw it where you have a partial double bond on each side. So, you know, it's half double, half single. So we're going to have it be a 1.5 bond. It's in between a double and a single bond there. So this would be your real structure, where you have this partial double bonds. So these bonds are really the same, right? They're the same type of bond. They're both a partial double bond, right? So you can even say that the bond order is 1.5, which means it's a 1.5. It's in between a single and a double. So it's a partial double bond. And those bonds are the same, okay? And so they should be the same length. So I've got this picture here. This is what ozone really looks like. And what this is showing you is that this bond is the same between this oxygen and that oxygen. These two bonds are exactly the same bond length, and so they've got to be the same type of bond. So it's not like it's a double and a single, right? It's not a double and a single. They're not different. They're actually the same type of bond. They're partial double bonds. It's an exact mixture of those two resonance structures. And it has a bond order of 1.5. It's a partial double bond right in the middle. So that's why the bond lengths are the same. Why are they equal? Because they are both partial double bonds. All right? They are exactly the same bond, right? Not a single and a double. Okay? It's not a single bond, it's not a double bond, it's exactly in between the two. Okay? So that's what resonance, so you know, this structure doesn't really exist, this structure doesn't really exist. What exists is the equal blending of those two structures and to give the real molecule, which we can call the hybrid structure there, which is a hybrid or a mix of the resonance structures. So let's do one more practice where we want to come up with the resonance structures of NCO-, and they're telling you that the carbon is the center atom there. It's a little bit harder to come up with your resonance structures here, so I'm going to help you out a little bit. So we can put a nitrogen, carbon, oxygen. So that's what it's telling you. That has to be in that order with the carbon in the center and then nitrogen and oxygen. Anytime you get resonance structures, do not move where the atoms are. All you're really allowed to do is to move electrons, is all you're doing. And let me just go back for a second. I just want you to realize when you switch from this resonance structure to this resonance structure, all you're really doing is you're moving the one pair of electrons. If you imagine taking this pair of electrons and moving it here, you would be making this double bond right there, right? And then you would move these electrons and move them onto that oxygen. So by just moving the electrons, you can switch from one resonance structure to the other. So that's what you're allowed to do in resonance structures. You're only allowed to move electrons and you're not allowed to move atoms. So in this structure here, let me give you a Lewis dot that would work. You could come up with this Lewis dot here would work. And let's get another resonance structure. We could imagine moving the electron from the triple bond. You could imagine moving these electrons up here to that nitrogen. And then, what do we want to do? If we do that, then what you need to do, when you move that one up there, you would have to move these over there. So let's draw what you get there. So now you would have this nitrogen with two lone pairs, double bond to a carbon, double bond here, oxygen, just like that with a double bond. And you can see that everything is octets, totally legal, legitimate there, Lewis dot. And now what we're going to do is we're going to move one more time. We're going to move a lone pair from the oxygen. I'm sorry, I'm thinking the wrong way. We're going to move this one now. What do I want to do? I want to get okay, so we're going to move this one over here, and then that's going to move electron pair. I'll move it this way. There we go. That's what I want to do, right? So you can move it over here and then move that one over there. That's going to allow you to get another resonance structure here. So let's see if we can write that one in. So now this nitrogen now has 3 lone pairs, which seems a little strange, and then we're going to have a triple bond to this oxygen there. You should see that everything still does have octets, so they are legitimate Lewis dot structures, but we do want to look now to see what the formal charges are, to see which one is the most stable. So again, you have to go through, if you want to practice, see if you can put in formal charges into these structures. If you want to pause for a second, put in your formal charges, and I'll do them really quickly right now. So this nitrogen has 1, 2, 3, 4, 5. Nitrogen usually has 5, so that's a 0 formal charge. This carbon has 1, 2, 3, 4, normally has 4, so that's good. Oxygen, 2, 4, 6, 7, that's 1 more than normal, so that's your negative on the oxygen, which is good because there's an overall minus charge in the molecule. Over here, 1, 2, 3, 4, 5, 6, that's 1 more than normal, that's negative. Carbon has 4 as normal, 2, 4, 5, 6, oxygen is normal. Nitrogen, 1, 2, 3, 4, 5, 6, 7, that is 2 more than normal. So minus 2, 2 more than the normal 5. Carbon has 4 as it normally does. 1, 2, 3, 4, 5, only 5 assigned to it instead of 6. So that gives us a +1. So overall, that is giving us the -1 for the overall molecule. So that is correct. So there are your formal charges. Obviously, this one is the least. This one here is the least favored. That one's probably so unfavored it's not going to exist much like that resonance structure. So we want to look at these two. Both of them have just one atom with a -1 charge. So you might think that they're equally favored. But if you look up here, there's one more little caveat as far as formal charges go. Up here at the top, it tells you that when you're doing with formal charges, you want to put the negative formal charges prefer to be on a more electronegative atoms, right? So if you have to have a negative formal charge, you want to put it on the more electronegative atom. So let's see if we can figure that out. So if we go down to the bottom here now, which one is more electronegative, oxygen or nitrogen? Right? Whichever one is more electronegative, that's the one that's going to be more favored. Oxygen is more electronegative than nitrogen, so this is going to be the most stable structure because least formal charge and least formal charges and negative is on more electronegative oxygen. Right? There you go. That should do it. That is how you come up with resonance structures and putting in formal charges. Thanks. Bye.